we're going to look at Chapter 16, Rifting, Seafloor Spreading, and Extensional Tectonics as a whole. At the beginning of the chapter, we're looking at, what is rifting? Rifting is when the land, the crust, is splitting apart. A rift system is where continental lithosphere is currently undergoing extension. So over here we can see Eastern Africa, and there's an East African rift system where currently extensional activity is going on. It's going on right now as you listen to this lecture, and it's been going on for a long time. Parts of it have stopped. Most of it is still actively spreading. You can see there are multiple legs. It's not just a simple straight line. Remember, we're dealing with the surface of a sphere rather than just flat things on paper or on a computer screen, and so movement and tearing and subduction all happen with curves and multiple lines intersecting to spread it over a spherical surface. Here you can see an aerial image of the same region. You can see Lake Victoria in the image and in the map drawing. And you can see to some degree where the rifting is, especially where there are these long linear lakes that are in the low areas caused by the rifting. An inactive rift, on the other hand, is someplace like southwestern United States. Here, if we look at the aerial image, the satellite image, we don't see the long lakes. We do see some rivers, of course, like the Colorado River. However, it looks noticeably different from the image over in Africa. So that's an active and an inactive rift system. So taking and looking at the, really simplified map version, we can see the area we were looking at before, and we can see that that rift system extends far beyond just the southwestern U.S. And this lets us introduce a new term, an allocogen. An allocogen is an unsuccessful rift, specifically a rift cutting into a craton at a high angle to the margin of the continent. So here we have the margin of the continent, the west coast, and you notice that these are at a high angle. They're not necessarily all perpendicular, like the Unta allocogen is basically perpendicular to the west coast, but these others are still at high angles. They're not parallel to the coast. And so you can see there are numerous allocogens within the continental United States, and there are others north and south of us on the same continent, up in Canada and down in Mexico. And then, of course, every continent has some of these. Here we can see a photograph of an allocogen. This is part of the Grand Canyon. So what's going on when there's rifting? We can start out with a nice basic chunk of lithosphere. The moho is fairly even. It's a nice flat section of land, no mountain range, no big rift valleys or anything like that. It's just basic, hypothetical, perfect crust and lithosphere. And we can see this length before rifting. So like if we built a little house here and a little house here, they're that far apart. Now, these imaginary houses are super durable and last for millions of years, and after some of the rifting has completed, they're now much further apart from each other. The lithosphere has stretched. With that stretching, it's thinner. It changes where it's floating on top of the asthenosphere. And so since it's so much thinner, it doesn't ride as deep. And we have the asthenosphere pushing up into what, it can't form a gap. So the asthenosphere is rising up into that, under that thinned area. And above it, we do effectively have a gap, of course. Atmosphere is filling it in. And then over time, sediment as well. So we have a thinned lithosphere. The moho rises because of the thinning and the uplift that's happening. It pushes the moho higher. And then eventually, after the rifting is far along or even complete, we can have something like this. This is an actual cross-section from the Shetland Islands over to Norway. And you can see the center of the rift area is much thinner. The moho is higher, just like in the cartoon drawing on the previous slide. The ground surface is lower. It's filled in with lots of sediment and then covered with water at the top here. And that's the sea that we can see between the Shetland Islands and Norway. So, what kind of structures do we see in a rift? If you see a geologic drawing of a rift or a discussion about a rift, what kind of things are you going to see? What kind of terms are you going to hear? Well, Horst and Graben is the most common pair of terms that you'll hear anytime a rift system is being talked about. In a perfectly symmetric rift model, where it's spreading evenly, thinning evenly, everything is, hypothetical and perfect, you get this really regular Horst and Graben type formation. So this structure, the Horst, is where the normal faults are dipping away from each other. So here is a normal fault and a normal fault dipping away, so this is the Horst. A Graben, a pair of normal faults dipping towards each other. So here's a fault dipping towards each other. That's a Graben. I will show you a much easier way to remember that in just a moment here. But this is the basic Horst and Graben structure, where you have alternating hills and basins. So how do we remember which is which? Trying to remember which way the faults tilt isn't necessarily all that intuitive, but this is a little word game that I actually still use myself to make sure that I'm remembering these perfectly right, and I've been telling students this for years. You can ride a Horst like a horse, and Grabens look like little trolls under the ground are grabbing them and pulling them down. So you just picture a cowboy sitting on top of that Horst and a troll grabbing it and pulling it down. However, in real world situations, not many rifts are symmetric. They don't follow that perfect pattern. What they are is asymmetric. Makes sense naming wise. Hey, if it's not symmetric, it must be asymmetric. But what does that mean, really? Well, it means that instead of just alternating directions of faults, there's a whole bunch of faults that all go in the same direction and merge at depth. Basically, you've got a big fault, and then you've got a bunch of little faults that feed into it, and sometimes even more small faults that feed into those. This bottom here is called a detachment. Basically, the whole thing can slide across that. And you get fill, and you get angled edges or corners of these fault blocks instead of the whole fault blocks standing up. And so we call these little triangular depressions, or triangular, basically basins, half-grabens. Because one side of it is a tilted fault, the other side is the old ground surface. So it's only half of a graben, so we call it a half-graben. And instead of horsts, we have these ranges that are just tilted blocks. In the classic symmetric system, the horsts are the ranges. In this case, they're not horsts, they're just the corners of each of the fault blocks. So, what kind of faults are those? They could be planar, or they could be listric. Either way, they're normal faults, but the difference is listric faults are curved. And then planar faults, of course, are planar. They're straight lines. So if we take a bunch of faults, all straight lines, and then we collapse it and try to move them, we end up with a bunch of gaps. Well, you can be pretty sure there aren't giant gaps under the earth just sitting there empty. It's not going to happen. Rock is going to collapse. Things will not form giant gaps like that. On the other hand, if we have listric faults and we slide them along these curves, we end up with something like this, and we don't have gaps. So logic dictates that the listric faults are more likely. Also, when we go out and we do geophysical surveys, like seismic surveys, we can see the faults, and we can see that for the most part they are listric. There can be some planar faults mixed in amongst the listric faults, but overall the primary fault type in this extensional system are listric faults.